Okay, let's go ahead and get ourselves going. So welcome to CEE 120 220C. Kind of a new class, something that we've always wanted to do that kind of demonstrates where the technology with all the BIM and building information modeling is going, and kind of looks at how we can actually use parametric design, which is actually underneath a lot of what we do in BIM, really to our advantage to be able to kind of just test out all sorts of different scenarios very quickly and really try to find the best solutions of all the different range of solutions that are available that we can test through the design software. So we'll get into what the class is going to be all about in just a second. I wanted to make an announcement though for anyone who might be interested of an opportunity to do some as-built modeling using Revit. And I have a colleague at Autodesk who is a really cool old Victorian house up in Oakland, and she's just looking for someone to come through and do some as-built modeling in Revit. I've already done kind of a preliminary model, but they want to do a little bit more detailed modeling on it. So it's one of those things, if you have a couple hours available on the weekend and be willing to go up to Oakland, she's willing to pay. So it might be kind of a good little kind of part-time thing, and she wants to kind of keep on going with it in terms of doing some energy modeling on the house. So if anyone's interested, let me know, and I'll put you in touch with Dawn. You actually a cool little opportunity on the side. Okay, in terms of what we are going to be doing, let's talk about that. Close all these things up and see if we can make this work. Okay, at a high level, what we're going to be doing is using parametric modeling software to really go ahead and focus on what I'll call performance-based design. And it's really this whole notion that, as we go through and do our design work now, we can really start looking at a lot of different criteria and comparing those different criteria or the performance of our building against those criteria to really come up with better solutions. And it's not just about kind of coming up with a single solution that is aesthetically very pleasing or meets a single criteria, like is a very good energy performer, but you can actually start looking at a whole range of different options and consider those options very systematically to really try to figure out really what are the ones that do the best job of meeting multiple criteria, and ultimately how you think about how you want to trade off those different criteria. So in terms of what we're going to be doing in class, it's really going to be breaking down into kind of three distinct phases. We're going to spend some time up front looking at the whole notion of how we explore different forms. So just given the fact that we have modeling software, we've been doing an awful lot of what I'll call direct manipulation so far. We kind of push, we pull, we set the parameters, we just create the form that we want, but we do it in sort of a very one-way method. We have a design intent, we sort of encode it in what the model is, and the model pretty much carries that intent from here on out. What we're going to start doing is thinking about all of those different decisions as being sort of more variable, and how you can make those more variable and control different sliders to let you experiment with a lot of those different options and see what the impacts are. So we're going to spend some time up front just thinking about how we model things in a way that lets us explore them very easily. Yeah. Then we're going to think about really the whole notion of how we want to go through and evaluate them, and how we can use software to provide all sorts of different answers to how we're performing relative to those criteria. We'll talk about those in just a second. The third big phase is really going to be all about thinking about optimizing, and that is, given that you can evaluate a building design against a criterion, how do we then go through and kind of look at several different options and narrow in on the best performing one? Okay, so for example, if it was a building and we were looking at, the amount of solar radiation the building could collect, we could try all sorts of different things, like rotating the building around to different degree increments and see how that does. Or we could try raising the slope of the roof or lowering the slope of the roof or the panels on the roof. And just kind of play with different parameters and see really which of the different combinations of parameters really gives us the best ability to collect solar radiation. Okay? But we can really do that for any criterion. So the idea is we'll start thinking about how we can set up little programming loops, little iterators to go through different cycles and get answers out of the evaluation software. Okay? Compare those and then really drive towards the optimums that we're trying to look at. We'll look at it in two ways. We'll look at it in terms of both thinking about a single-dimensional type of optimization as well as thinking about multi-dimensional. What if you have two different criteria that you're trying to trade off? And how do you sort of navigate that space? Because one thing we're going to figure out pretty quickly as we start exploring different spaces is that the total design space of options is almost infinite. And we really start thinking about all the variables and the different things we can adjust. There's almost an infinite number of potential design solutions. So the whole idea of how we really narrow in on the ones that are the most meaningful along multiple criteria really gets to be pretty interesting. And there's a lot of different good models we can use. You know, there's some really promising research that's going on, using kind of biological models and almost using, like genetic selection algorithms for figuring out what are the strongest options that we found so far. And based on those, if they got together and bred, what would actually sort of be their children and their grandchildren. Yes, we kind of create other new options that are sort of exhibiting the most favorable traits. Okay, so really, really cool stuff to come. But in terms of getting going, let's just stop for a second and think about the whole notion of evaluating, how we even want to sort of approach that. And I suggested there's lots of different ways of kind of looking at this. But I just love to kind of think about as a starting point just some of the different criteria we could be using to go through and evaluate any design. Like architecturally, I often think about, the aesthetics of the building, things that make the building desirable kind of in an aesthetic sense. So let's go ahead and give it a real context, just sort of put it out there, make it a little more real. Let's say, for example, I gave you this fantastic waterfront site in San Francisco. So near the Bay Bridge, kind of overlooking the bay, kind of in a dense urban environment, something like that. Okay, so aesthetically, we can come up with any number of building forms that might fit within that space. We'll have some small lot, we'll have a certain amount of space, we'll have some neighbors, all sorts of things. But as we think about a design problem like that, and you can also even sort of think about sketching out a few of your own ideas as we kind of do this. What are some of the aesthetic criteria we might use to judge just how well that building is performing? Any ideas, like as you think about a building aesthetically, what makes it good? Okay, or in a way that we can sort of talk about it numerically.
Proportion.
Yeah. So there could be some sort of closeness to kind of I'll call like pleasing proportions. Okay, that's one thing that often sort of really kind of increases its attractiveness. Other things that people often think about in spaces like this, from an aesthetic standpoint, there's this whole notion of how many closeness to windows. So how much of the space is close to an exterior window so you get to enjoy the view. So you could say, it's things like, kind of closeness to views. Yeah. What are other things people care about in offices? In buildings like this. Yeah. Are you aware of sort of the corner office syndrome? That everyone sort of wants the corner office, and actually we sometimes optimize buildings towards that. If you look at some buildings like the Petronas Towers, they actually have an awful lot of corner offices, or the Bank of America building has a lot of corner offices. It was really done as a big seesaw shape, just so that we could actually go through. If you looked at the bad marker. If you looked at the Bank of America building, for example, in plan, it actually does this. A lot more of them. That's a bad design. But basically, everyone has a corner office, which is really kind of a nice thing. Okay, so there's the whole corner offices. How about if we're on the waterfront? Okay, is there any sort of bias towards offices that face the water versus offices that face inland? Okay, so we can kind of look at it that way. Okay, views of the water. We can look at it in terms, what else makes an office desirable? If you were going to try and sell an office as being kind of incredibly desirable, or space as being very desirable from an aesthetic standpoint, what are other things that sort of make it better?
High ceilings.
Okay, excellent. Oh God, yeah, high ceilings. I can put another one in there. It's kind of this feeling of grandness. Whatever it's, yeah. No one likes to feel like they're all closed in a little cube or something like that. Okay. So there's a lot of things we could be looking at. And the idea is what we want to do is come up with ultimately metrics, different sort of numbers that we can evaluate, or different measures that we can evaluate the building by, so that we can then ultimately really judge whether or not the building is performing or how well it is performing on that. So if on a scale of a 0 to 100 we had to rate the building, okay, we could come up with some sense of why building A is better than building B. Okay. There's lots of other ones. Like if we were thinking about a building not strictly from an aesthetics viewpoint, but we were thinking about it in terms of just how it's addressing the sun, like what are some criteria that come up there? Like one of the ones that I sort of mentioned a little while ago was the whole notion of, oh, it's kind of your solar capture potential. And different buildings will have for different amounts of that based on like their orientation. In fact, we can even sort of get clear about that. There's different things we could look at there in terms of trying to vary that. We can look at the building orientation. We can look at the notion of the surface slopes. Yeah. How about, so we can think about the sun in a positive light. Yeah. What's the criteria that might actually make a building a negative performer from a solar thing, from the solar potential? So as we think about buildings and sun and how they address the sun, what would actually make a building less desirable? Anything?
Huge southern glazing.
What's that?
Large southern glazing.
Oh, it could be, okay. So we could say that if like the solar gain is like too great, which would be indicative by like or one way that we can get that as too much southern glazing, that could be a problem. Okay. Another criteria we often use when we're addressing buildings is this whole notion of how we impact our neighbors. So if somehow our shade is casting a big shadow on our neighbors, that's often like considered pretty bad. So okay, we have to look at sort of the whole issue of solar shading. How about from the wind standpoint? What can we say about the wind? What makes the building a good performer in terms of the wind or a bad performer in terms of the wind?
Orientation.
Okay. So talk to me about that. So what would make it good, a good orientation relative to the wind?
Something that kind of presents thin profiles where the prevailing directions are. So
Okay.
especially if it's a tall building.
So we'll say, I'm going to say like the whole wind resistance. Okay, and orientation will be one of the ways we can sort of play with that. Oh, and sort of the whole profile too. Okay, so orientation and profile. There are different things we can do with that. There's really some fantastic examples now of some of the most interesting buildings. Like one of the one building that's really quite interesting if you haven't paid much attention to it. Look into the Shanghai Tower, and it's the whole story of really how by working with the shape of the building and the profile that it's presenting and putting a little bit of twist in the form of the building, they were able to go through and reduce the wind forces on the building greatly, which ultimately led like to a 25% savings in the structural kind of members. Which is a huge cost savings, kind of very big environmental ability plus, or environmental plus in terms of the material impacts. So we can look at things like that. How about in a positive sense? What's good about a building in terms of the wind? Or what could we maximize about a building in terms of the wind? Yeah. We can kind of say, okay, whether we're kind of getting some sort of ventilation. Oops, if that gets spelled properly. What else could we do? We could look at a lot of buildings now just as an energy offsetting measure. We really look at the wind potential. Really, what is the opportunity for putting turbines on it, or so wind power potential. There's a lot of things we do that we can do in terms of optimizing lead performance. I think a lot of us do that as we start thinking about a building and really trying to think about things that might give us more lead points. Like, what are some things that actually, in a real high-level way, are good that we can adjust in terms of the architectural form that will then ultimately impact how many lead points we get? What are some of the lead points that we really try hard to get? What are some ones that are sort of very impactful, or what can we affect to it? It's just the architectural design.
Energy category has a lot of points.
Okay. So we could get to this whole thing. Actually, it's sort of funny. We'll say, just the whole energy use. That's ultimately going to kind of drive a lot of lead points.
I guess for lead, like in architecture, the facade design.
Okay. And what would make it a good performer from lead? Okay. In terms of the materials or the shading. So we can start evaluating a lot of different designs. We don't have to look, at the form. We can start looking at the materials in terms of, what percentage is recycled, which percentage is locally sourced. We can start looking at a lot of different things and evaluate our different designs, kind of based on those, which, just adds sort of more, complexity. There's a lot more variables we're playing with. And that's really, I think, the point of all this is really to start thinking about how broad all these different criteria are. And, it's funny, we sort of do this implicitly. We as designers sort of have this incredible array of all these different things we're supposed to simultaneously optimize and somehow keep them all straight in our head. And it's really pretty amazing that you can. What has often happened in the past is that since we really didn't have very good ways of evaluating the criteria, we sort of, well, that would be pretty good. We sort of give sort of vague general answers, and we sort of use rules of thumb and intuition to kind of guide us in terms of how we could use these things. But what's really changing now is that we have the ability through the incredible power available through modeling and the ultimate attention to the analysis tools to get real hardline answers. And all of a sudden, the fact that we have real answers raises our responsibility quite a bit in terms of like, okay, geez, now I actually have to be held accountable to this because there is a definitive answer about how much better or worse something is. And we can kind of get to those things. Okay. Structurally, thinking about it from that standpoint, the whole notion of wind and in the relation to structure is kind of good. Any other things that we would rather try to optimize from a structural standpoint? The answer is yes, there's a bunch of them. I'm just trying to think of any that we can sort of throw up on the wall really quickly.
Minimizing the size of the levers.
Okay. And when you say size, is it size or is it weight? Or kind of both, or?
Yeah, I guess it would be weight.
Okay.
Or, it could be both. Because, I mean, you want to minimize the weight, but then you also want, like, thinner members, right?
Mm-hmm. Mm-hmm. And why do we care about that? What's it really driving? Do we like thinner? Is it because we like less material, or we like less cost, or what is it that sort of drives that?
Like it allows you to have higher ceilings, and it allows more space for ducts.
Got it. Okay. More space for coordination. How about this whole notion of, all these tall towers that are built these days, the amount of sway that's in the tower, and like how much you really want to pay attention to that. Is that sort of entered into the design a lot too, or it's another one of these funny criteria that, depending upon where you want to fall, like on there, we can either build incredibly rigid towers or come up with all sorts of different strategies, to kind of deal with the whole issue of minimizing sway, which is especially big for big towers. Another one, you may feel it in the building here every once in a while, is there's this notion of springiness, okay, where as you walk across the floor, does the floor kind of bounce a little bit, or is it very, very rigid? And that's another one of these things that is actually, I don't know, it's a designed kind of consideration. As we do houses, deflection. We always sort of have this debate. Oh, do we want to use L over 360 or do we want to use L over 480? And it's really just this funny notion of just how springy things are, and it gets to both people's comfort as they move across something, because it turns out you're not all that comfortable when the floor kind of does a little flex. You're really good at detecting what's happening there. And I've been on a lot of like steel stairs where it gives us just a little bit more than expectation, which is that little kind of uncertainty and doubt, and that's a little bit rough. The other way that factors in is as buildings deflect an awful lot, then you start to have material cracking things. You have to sort of worry about the fact that the materials have to flex to go ahead and handle things like that. How about from a construction standpoint? If we were thinking about constructability, are there any sort of like big criteria we'd throw out there? What do we try to optimize as we sort of as we plan our building and think ahead to construction? What sort of things make a building better than other buildings?
Scheduling time.
Okay. So it could be this whole notion of really Time schedule to construct. Say again?
Crash detection.
Clash detection, okay. So this kind of whole notion of minimizing clashes. Actually, one that, some of the research at CEE is really making me very aware of the whole degree. It's kind of the degree of prefabrication. Like, how many parts are in the building and stuff like that. And there's a lot of different approaches we could use that have a big impact on the number of parts that are out there. So I'm going to say prefabrication parts. There's just, and I guess the point of all of this is really that, there's just any number of criteria. And again, what's really happening is now that we have the ability to sort of start looking at all these things and we're working on cross-disciplinary teams, we have a lot of different people who bring expertise to the table. It really does get to be a little bit hard sometimes to go through and figure out, what is the best solution? And the truth is, there's rarely a single best solution. There's often a whole range of different solutions that are pretty good, some of which are very closely clustered, some are sort of very divergent from each other. But we want to sort of be evaluating all those and understanding why we're making those decisions. And one reason we need to kind of think about that stuff and actually thinking about it in a very dynamic way is, and this kind of gets to the difference between direct modeling and where ultimately parametric modeling helps you out. If the world were static, okay, and things always cost the same and never changed, and we could actually lock things in, you could say that making a decision once is good enough. Okay. But what's happened so much in the world these days is things actually change pretty rapidly. So it's actually even more important to understand what your design intent was than the actual decision you made. Because given the same design intent and a different set of input parameters, you might come up with a completely different decision because some material got much more expensive or was going to be delayed, or some new material came out that has much better performance than the old material we chose. And you sort of really want to understand what was your driving consideration, almost more than the actual decision that you made, so that you can reevaluate. Because in that life of the project, if we're going to spend 3 or 4 years building this, let alone the lifetime of the building, things might change and we might want to change, kind of re-optimize based on those things. Okay, cool. And that's enough to get us going in terms of thinking about the space. Let us go ahead and think about how we start applying all this. So that's where we're kind of going. It's really this whole notion of we're going to spend some time together first exploring. We'll probably spend about the first 3 weeks really looking at exploring how we create lots of different forms and can control these easily. We'll spend a couple weeks, I'll give you a more detailed syllabus about this, we're looking at how we basically bring that information into analysis packages to go through and provide results for us that we can then use. And then we'll finish up by just looking at the whole notion of, given that we can get answers back, how we then guide ourselves towards more optimal solutions, getting a range of solutions. Okay. In terms of what we'll be doing in the class and how we're going to be working, I would sort of lay it out something like this. I think we're going to have, and this is always, anyone who's ever been in one of my classes knows this always changes. So this is the general format we're trying for right now. I think what we're going to do is get you started with what I'll call little mini projects, where it's going to be more little programming assignments that are pretty contained in terms of what they're trying to do, just as we're building our skills and working with Dynamo and working with Grasshopper, just kind of little things to do that are sort of all about just learning how to use those platforms and start to exercise them and get some definitive results. Towards the end, though, we're actually going to go ahead and have you work on what I'll call an integrative self-design project, where really you'll get to choose something that you want to do some parametric design to. Okay, and then apply what we've learned so far to that. So it builds towards the end, ultimately you deciding really what you want to do, what aspect of a building you might want to optimize, or it could be a product, it could be something else, but it's really, you'll get the choice of really trying to figure out what you want to do with that. Okay. In terms of logistics for the course, some different things you need to know. You can register for 2 or 3 units in Access, whatever sort of makes sense for your schedule and your restraints and constraints and all that kind of stuff. So please sign up there. We're going to go ahead and work with Raj on our teaching team and Demi on our teaching team, and hopefully Patricia on our teaching team, so we get that set up in terms of getting that all working. Viewing options, we are going to be kind of live here Tuesdays and Thursdays from 9 to 11 essentially. But we're also recording everything, so it's going to show up online again too. So for people, I know several people couldn't be here today, or as your schedule doesn't allow you to be here at different times, things will always get posted ultimately to YouTube and through the site, and it'll be available that way. And that's A-okay. In the scheme of things, it actually worked out. It was actually, it's sort of interesting. I make an observation to some of the other folks I work with about the whole notion of the live versus the online. And I see very little difference in the results between people who just take it online and take it at your own pace and people who are actually here in the classroom. And it's really, I think it's actually a really cool thing that it sort of just works pretty well one way or the other. So I don't think people are really disadvantaged other than my slowness in posting videos. But Raj is going to stay on top of me in terms of getting that done this time. So yeah, I think that's perfectly valid, and if that's a better way for you and your timing, feel free to do that. The only danger I'll warn about relative to the online viewing, because I think it's easy to fall into this when you're doing it the online way, is just keeping up with the assignments. Because, and I think most of you know who've ever taken a class, I think everyone has, who I recognize here, has taken the class the day before. The whole notion of, in general, everyone does okay in terms of grading and evaluating. It all sort of works. The only thing that you ever get in trouble for in the classes is just because you end up falling behind, you just don't get the work done. So it's one of those things, just try and stay on top of it. That's the most important thing for all this stuff, because between now and June, it's all free and easy now. It all looks good, but you know what's going to happen in the third or fourth week when you start getting busy and all the different assignments from all the different classes and midterms come around and stuff like that. It's just tough when you start getting behind, and it's really hard to get back on top of it. So please just try and keep up, and if you do, the online ought to work just fine. For communications, we will go ahead and set up the coursework website. But actually, last quarter we played around with the whole notion of the Google Plus group. I kind of liked that in terms of just a way of people posting what they were up to, the videos are there, and people put questions up there and examples of things that were in there. So I'd like to go ahead and use that again. I actually think that was like a pretty good way of doing that. So if we're going to do that, for most of you I already have your Gmail addresses, but I don't. If you haven't been part of a Google Plus group last quarter, go ahead and just send us your Gmail address, and we'll get you added into that. I think most everyone's already there. Okay, any questions on the logistics? Sort of make sense? More or less? Okay. As much sense as I ever make. It always starts out one way and it adapts along the way. So, but that's okay. We're in this together. And this is new and experimental. So, that's whatever. It'll have a give and take because of that. Yes?
Will there be another live option? Or like another class time?
It's, well, let's kind of, I'm always open to like times and stuff like that. So, let's talk about how well this time works for most people, or if there's any sort of like interest in scheduling for a different time. Like, currently Tuesday, Thursday at 9 to 11. I'm pretty flexible about what we do in terms of doing that. Is this time not work so well for you? So you're thinking of other ones?
I have a class at
Okay, so we need to get you out of that. Do a lot of people have a class at 10, or what do we have in terms of trying to get a sense? Do most of you stay from 9 to 11? Okay, so it may work better just to kind of come for the beginning and pick up the tail end that way. Okay, no worries. It's always a tough one because it's like this. It's one of those little puzzles where as soon as you move one thing, it messes things up for other people in other ways and stuff like that. So it's very tough.
Is there only one project assignment?
Oh, for this class?
Yeah.
No. There will be a series of smaller things. So what's going to happen is, for the first couple of weeks, we're going to go ahead and do smaller things. So we'll do things where, for next week, you'll do kind of a small chunk that exercises programming in Dynamo. Then we'll do something else that does a little bit of programming in Grasshopper. Okay. But then I say we're at midterm time through the end. Then we'll switch to be more where you get to choose a design problem you want to work on, and then you follow that one through.
What's the final project?
Yeah, that'll be the final project? Yeah. So we'll work that through. And then, as is typical, there won't be midterm or final. It'll all just sort of be based on ultimately presenting your project at the end. Okay. Any random questions about logistics? Or very good questions about logistics? You can devise it that way. Okay, great. Then let us do a little bit of mucking around with software, and then we can actually get going with some stuff. Yes, Mr. Raj.
The prereqs for this course, are we still thinking of, people should have taken 220 ALB?
Yes, in general, although I'm looking around the room. Has anyone here not taken BIM modeling? I think I recognize everyone. Everyone's taken like 110A or 120A or something like that, right? Yeah, I think, right? Okay. I believe we're there. Okay. It's what I would say, 120A, 110A, not a strict prerequisite in that you could go ahead and like take what we're doing, just without all that, but it's a very helpful background if you have it there. So even as you're talking to other people and people, are asking about the class and stuff like that, yeah, I'd say it's recommended but not 100% required. That makes sense? Okay, beautiful. For software, let's do this. We're going to be working with a couple different things to get ourselves going. We're going to start with Revit and Vasari and working with Dynamo. And actually, Revit and Vasari, either one of those will work with Dynamo. Revit and Vasari, in many ways, are really the same program. They just kind of have different sort of features built around the edges. It's the same core engine behind the two programs. So you can either be working in Revit or Vasari. Most people, I think, already have Revit on their machines. Dynamo is something that would be very helpful for you to download to your machines. So if you can, please, let's head over to that site either on your machines or actually on the machines that you're sitting in front of if you logged into those. And let's just kind of take a look at what we need to do there. So I'm just going to go to Vasari. Actually, I could say Dynamo. That'll work too. Download. And it'll take us to this site. It'll be Autodesk Vasari / Dynamo. So AutoDeskVasari.com. And what we want to do is just download that extension. And now we'll go ahead and put some stuff into your Revit environment, your Vasari environment. Let's take a look at what that looks like. It'll download some incredible exe file, I think it is. Dynamo exe right there. And once you have that Dynamo exe, just go ahead and run that. And it should install for you. So I'll go over to my Windows environment and see if I can download that. So I'm going to come over to, my downloads. And I'll find there's the Dynamo install. If you can, just go ahead and run that, and it'll put it on your machine. Okay, so go ahead and do that. We'll show you what it does. It actually adds a very little bit of extra stuff to your Revit environment.
When we're asked to select components, I assume we should also choose Dynamo for Vasari Beta 3 when it says components to be installed.
Yes.
Okay.
Get them all. It'll basically suggest everything that you have on your machine that it can recognize. So if you have Vasari on there, if you have Revit on there, looks like I have Revit 2013 still on here somewhere, where it thinks it is. So just go ahead and install all that. It'll do a little bit of work. It's actually a very small little installation. And that is about it. Okay, so if you can install that, that'll just get us going. And let me tell you about what Dynamo is, just so you get a sense of where it fits into the big picture. So we've been working with Revit, and Revit, a lot of you know, is parametric, in that as you start changing different values for any of the different properties of an object, any instance properties or family properties. It'll stretch, deform, it'll change its behavior, all those things thought of as parameters. So what Dynamo really does is it gives you a visual scripting interface that lets you quickly change those parameters. So as opposed to having to go in and open and change and apply and open and change and apply and open and change and apply, it just gives you a scripting interface that will actually do that for you. And that ability to script and change things programmatically is really what gives us the speed. That you can really start changing a lot of different variables, seeing what the results are. And this programming language gives the ability to connect between different programs and say, hey, give me an answer to my design problem, bring it on back so I can actually evaluate whether or not this is a good solution. Okay, so we will experiment with that in the next little bit, but let's see how we're doing in terms of the install. So did the install come down on most machines? You good? Okay. Let's see, I'll tell you how you can, we can see that it really has worked for you. And how that is if you open Revit on your machine, just open that up. And we will take a look. Okay, Revit is hanging around there. Let me open up a project. I'll just open up a new blank project. Doesn't really matter which template for what we're doing today. Revit won't look very different in most senses, but it will look a little bit different in this way. If you go to the Add-ins tab, you should see something that says Visual Programming. It has Dynamo under there. So let's see if you have that, because that's really what we're heading after. What's going on here? The taskbar is trying to tell me something, and I don't want to see it right now. Make it a little bit bigger. Okay, so let's just check in on how you're doing. Do you have Dynamo listed as one of your options under add-ins? Okay, you doing good? Everyone feeling pretty good about that? Okay, no one was doing right up front. Super. Okay, let's just pause there. We're going to get to Dynamo in just a second. Let's start though, before we even get into Dynamo, just think about parametric design and really, the ability to go ahead and use it and like how powerful it can be. And to do that, what I'd actually like to do is actually open up an example of some little parametric models of towers. Okay, and just kind of play with them for just a little bit and kind of along the way towards what we're doing. So if you've downloaded that link to the files that came through the Google site or came through ultimately through my Dropbox, go ahead and go out and open up the folder. There's a session 1 folder. You might need to unpack that. And under parametric towers, there's a couple of different little models there we can take a look at. I'm going to open the one called Example Parametric Towers. So if you can, open that up and let's take a look at what's going on. Okay, and at first when you open it, it won't look very exciting. It should look like a big blank screen. But we'll go ahead and make it a little more exciting here today. Okay, so if you have that file open, what I want to do is just add a couple of masses to the environment. You'll see I have a couple different masses loaded in here. There's a twisting rectangular mass and a twisting triangular mass. Let's go for the rectangular one first. I'm just going to drag that on in to my workspace. It's going to say that it needs to show the masses because they're typically hidden. We'll say OK. And let me zoom on out so I can start to see a little bit better. Okay, but there's a little mass, a little form that we could then make a building out of. Okay, it's actually quite a tall one, but we'll take a look at all the different properties of it. Let's see if you can get that mass out there just on the floor, and we'll take a look at it. So, how are we doing in terms of bringing that in? Am I feeling good? You got the mass? Excellent. Okay, so here's the deal. This mass is actually defined parametrically. So not only can we kind of twist and deform and do things that we did through direct manipulation, we can actually go through and change it very quickly using some of the parameters. And why we would like to do that is, compared to what we have done in the past, where I say, let's create a mass, and I create some sort of a box or some sort of form, and I say, let's go through and make a form out of that. Then out of that, I can start bending and twisting and whatever it is I want to do to it. Okay, that's direct manipulation. What I'm doing right there is there's no real memory of it. You know, the finished form is whatever the form is, and if I need to go back and start changing that form, I have to go back in there and start pushing and pulling and re-editing and stuff like that. But I really don't have very much control over it. Whereas my friend right next door, if you click on him, you'll see there are actually all sorts of different parameters that are kind of hanging around in here that make it pretty easy to deform him. So for example, right now the building is 200 feet tall, the base is 50 by 50, the top is 50 by 50. And go ahead and just try changing some of those things. So let me say that no, I really want a building to be 400 feet tall. And as soon as I apply that, that gets quite a bit taller. If I say 600, that gets quite a bit taller still. I can also start playing with the other parameters. For example, right now the base is pretty skinny. It's only 50 by 50. If I go through and change, there's a base width and there's a base depth. So if I change, for example, the width to be 100, I can very quickly deform the shape of the building. I can make it incredibly skinny by putting a very small value in the other direction. Same thing at the top there. I could make that 100 by 40 or something like that. And start looking at different shapes of buildings. Now, the fact that I have a parametric building doesn't mean that I have to be doing all this twisting and deforming. The fact that I have the parametric form can be used just very, very plainly. I could go ahead and say that really, let's see if it'll let me do a zero twist. I'm not sure if it will. Let's see. It will. Okay, so great. If I have that and, I say that's 50. Actually, let's make it perfectly rectangular. Yeah, I can use this parametric mass to create a perfectly plain, ordinary shaft, and that would be okay. It's kind of like the Hancock Tower or just some very kind of standard building that gets built today. Just a very flat rectangular form. But by putting the parameters in there, I now have the ability to start tweaking it a little bit. So I can make that 100 by 100 down at the bottom, give it more of a triangular form like that. I can play all sorts of games. I can do things like, even in here. What I want to do there. Okay, start tweaking. Again, yeah, all the different parameters create a infinite number of towers. And start playing with these, you can really easily come up with things like the new Freedom Tower. You can come up with almost any modern building that's being built today by just sort of tweaking around with those parameters. As well as, if you want to have some fun, try putting a little twist on the building. That's what I kind of like to do. So whether you want it to be a 30-degree twist or a 45-degree twist, whatever it is, you can start twisting the building around. And as you do this, okay, you might notice that the building's actually reporting a lot of information. Down here, we are always constantly getting information about the surface area. We're getting information about the gross volume of the building. We're always getting information reported out about it. And if we have some mass floors in here, we get even more information about it as we twist and deform what the total floor plate area of the building is. So we can really just kind of keep on reporting things and change things very quickly. Now, the key to making this work is this thing has actually been set up with some parameters. And from 110A or 120A, you might remember we sort of spent some time looking at how you add parameters to things. So in this form, if you say you want to edit the family, you can actually see what the parameters are. And you'll see that in this building, let me just take a look at it in the floor plan view. It might be easier to see there. I have lots of different little parameters set up. I have reference planes set up and parameters that drive the top width and making sure that they're equally spaced around kind of a center point. We have things that are about the base width. And ultimately, the one that really makes this the most interesting is this guy over here. It's actually the twist. So we actually have one of the reference lines moving around, and we can control the degree to which it rotates. And that's how we get the twist width. But really by putting, there's really, what is it, 5? There's 4 plus twist, I think, on this one. So I think there's 5 parameters that really control the entire shape. You can take a look at them all in there. Oh, I also have the height. So that's the 6th parameter in there. Okay. I really can get an incredible amount of flexibility in terms of adjusting this building and kind of making it all hang together. I could, if I wanted to, also introduce some formulas. So for example, if I knew that I wanted the top, either the width to have a relationship to the depth, or the top to have a relationship proportionally to the base, I could also build in formulas like that too. And we saw that. So for example, if the top width always wants to be 0.5 times the base width, I can do that, and it'll build in a formulaic relationship between those things. Okay, so parameters give you all sorts of just really flexibility to really quickly adjust and kind of have different behaviors that model really what your design intent is. So now it's always skinnier at the top as opposed to down at the bottom. Okay, let me close that up. Let's bring in another building though. That's kind of a little more interesting. This rectangular twisting tower is kind of interesting in its own right, but I don't know, it's got limits to what it has going for it. Let's take a look at another one that I think is a little more interesting, and that's this triangular mass. And you can bring that guy in if you want. This one is actually a little closer in form to the way the Shanghai Tower is actually built, where it has a series of different curved faces that are coming together, almost like a guitar pick. So there's a little triangular surface in terms there. But even for this building, there's still this notion of some basic parameters, or of this form, and we can take a look at that. We have, and it's really just depending on what I set up in the model. I have the top height, I have a height kind of in the middle of the building, and I have a base. The base is right at 0 right now. But I have a degree of rotation and a radius at both the top, the mid, and even at the bottom. So I really have like 3 bands that can sort of twist around to any degree of curvature. But let's kind of take a look and see what the effect of that is. So we'll focus on this building right now. So if I wanted to have a tower which was perfectly even going up and just have the twist, I can say that the base radius, the mid radius, and the top radius are all the same. Okay, and if I want to make it a little twisty, so it doesn't look nearly as funny to you as you look at it. That's a little bit closer, oops, to what may be familiar. If I wanted to go ahead and taper it down, for example, if I was trying to model the Shanghai Tower, what I would do is I would actually have the top radius be a fair amount smaller than the base radius. So 80 is, well, 80 might not be all that bad. Let me make it 100 at the bottom. Maybe 90 at the midpoint. And 80 at the top. That'll give more of a taper that's going up. Now, in addition to sort of the taper, there's also a little bit of twist to that building. And if we want to take a look at that, we can also start to control the twist. So, maybe for the mid-rotation. Actually, the Shanghai Tower kind of is an interesting story. It actually twists 120 degrees, I found out. They actually wanted to twist it 180 degrees, but that actually created a lot of constructability problems in terms of how the columns and everything have to line up to actually support that. So after a lot of consideration, they came up with 120 as being what they thought of as an optimal twist. So let's go ahead and try something like that. I'll put the mid rotation, at like 60 degrees. and the top rotation at like 120. Let's see if we can make it look similar. Now, that tower is actually quite a bit taller, just so you get a sense. Who knows what the height of it is? It's somewhere around like 2,200. It's over 2,000 feet. Okay, maybe the mid radius, I'll put it about 1,000, just kind of so it's evenly split. Now, I believe oh, that's the building got very fat there. So I think I made a mistake right there. The mid height should be 1,000, and the mid radius. Okay, never mind. But in the spirit of the power of parametric modeling, it's pretty cool that I can vary for something that's so incredibly round and bulbous to something so slim and like a tower-like very, very quickly. And I can take a model like this and now go into an analysis program and say, great, this is one of the options I want to consider. I got the 120-degree twist. Let's take a look at it from a wind standpoint, really. What's the wind resistance and what that's going to mean for the weight of the structural materials? I can take that and say, let's look at it from a solar radiation standpoint, really. Given this shape, what's going to happen in terms of the insulation that's in the glass and that we're going to have to ultimately deal with. Or even start to think about, based on how this building is oriented, it's not really necessarily completely uniform. You know, maybe I need to add shades to one side of the building based on the solar radiation, but not on the other side. You know, almost to, well, it's really almost sound like 120B, this whole notion that really as we move up to the tower, maybe it needs to become a very custom thing where different panels on different parts of the building are going to have different sizes or different shading distances or different fit distances to really go ahead and accommodate that. And that's the kind of stuff we can actually get to by doing this a little bit of programming. Okay, so we've been doing a little bit of just sort of notion of parametric modeling and taking a model that has some parameters associated with it and manipulating them directly. But the next thing we're going to do is say, hey, what if we actually wanted to go ahead and put a programmatic front end onto that so that we can get a little bit more quickly? Okay, so let us do this. It is like 5 after 10 right now. Why don't we break for like 5 minutes? Come on back in 5, and then we'll start the next part of it, which is really, okay, great. We understand revenue parameters. Let's talk now about where this Dynamo and this visual scripting front end comes in terms of giving you the ability to kind of manipulate things. Okay? So please join us again in 5.